If attention were the whole machine, the last episode would have finished the story. It did not. Attention can move information between token positions, but an LLM still needs a way to preserve what it already knows, transform what attention brings back, control the scale of those signals, and repeat the process without turning every layer into noise. The answer is the transformer block, a small computational blueprint stacked again and again inside the transformer-based LLMs that dominate modern AI. Not literally every language model uses one. Architectures such as Mamba take a different route, but inside a GPT-style transformer, this block is the engine room. One floor has two major working areas. Attention lets positions exchange information. A feed-forward network transforms each position separately. Two residual paths keep a running state alive through both updates. Normalization keeps the inputs to those operations in a workable range. That list sounds simple. The strange part is what happens when the same state survives dozens of floors. Start with a short sentence. The piano would not fit through the doorway because it was too wide. Every piece of that sentence has a position in a row. At each position, the model carries a long vector of numbers. Early in the model, that vector begins with the token embedding and position information. After a few layers, calling it an embedding becomes misleading. It now contains updates gathered from the surrounding context. So follow the position for it. The vector at that position is not a tiny box containing the word it. It is the current numerical state for that position. Earlier layers may already have written clues about the piano, the doorway, and the grammatical structure of the sentence into it. The whole row of vectors enters the block together. We will highlight one, but attention needs the rest of the sequence. On screen, the highlighted vector is a cyan ribbon running straight through the floor. That ribbon is the state the model keeps updating. Researchers often call this running channel the residual stream. The first operation does not replace the ribbon. It reads from it. In a common modern transformer block, the current vector is normalized before attention uses it. Normalization does not decide which word matters. It does not add meaning. It rescales the pattern of activations so the next learned operation receives a more controlled input. Think of adjusting a signal before sending it into a sensitive instrument. The relative pattern remains useful, but an extreme overall scale is less likely to dominate the calculation. Now, attention gets its turn. The previous episodes opened that mechanism in detail. Queries compare with keys, scores become weights, and value vectors are combined. At the level of the full block, its job is easier to state. Attention lets one position gather a learned mixture of information from other positions it is allowed to consult. For it, the attention update may draw useful information from piano, doorway, and wide. The real model does not move English labels along glowing cables. It computes vectors. Our animation makes that vector movement visible. Several colored contributions arrive, combine, and produce one attention update. Here is the first important surprise. That update is not the new state by itself. While attention was working, the original cyan ribbon took a direct path around it. At the end, the attention update is added back to the state that entered the sublayer. Current state plus attention update gives the next state. This shortcut is called a residual connection. It gives the computation a direct additive route through the block. Attention can contribute something useful without having to rebuild the entire representation from scratch. The shortcut is not a perfect backup file. Addition can strengthen one direction, weaken another, or partly cancel information already present. Later layers can change the result again. The honest picture is a running state that accepts updates, not an archive that guarantees nothing is ever lost. Our cyan ribbon now carries a purple attention contribution. The sentence has exchanged information across positions, yet the floor is only half complete. The next operation does something attention cannot do on its own. Each position now enters a feed-forward network, often called an MLP. Attention looked across the sequence. The MLP works on each position separately. Every position goes through the same learned function, using the same weights, but no position directly reads another position inside this sublayer. The cross-position information is already present in the vector's attention produced. The original transformer used two linear transformations with a non-linear function between them. The first projection expands the vector into a wider hidden space. The non-linearity changes which combinations can pass through. The second projection brings the result back to the model's original width, ready for another addition. Modern designs often change the fitting inside this workshop. LLaMA, for example, uses a gated variant called SwiGLU instead of the original ReLU feed-forward design. That detail matters when implementing a specific model. It does not change the durable mental model. The MLP performs a learned nonlinear transformation independently at each position. For the IT position, this workshop receives a state that already includes contextual information. It can reshape features in that state, amplify useful combinations, and suppress others. We should not label one neuron piano detector or one layer grammar floor. Real behavior is distributed and messy. The workshop produces a yellow update. Once again, that update is not allowed to erase the running state by default. The post-attention state takes another direct route. The MLP update travels through the workshop. At the exit, the two are added. Post-attention state plus MLP update gives the output of this block. Now the full floor is visible. Normalize a state. Use attention to exchange information across positions. Add that update to the running state. Normalize again. Transform each position through the MLP. Add that update to 2 learned transformations, 2 residual returns, 1 continuous stream. This is why attention alone is not the transformer. Attention handles communication between positions. The MLP handles nonlinear computation within each position. Residual paths make both operations updates to an ongoing state. Normalization regulates the signals around them. There is one complication. If you open the original 2017 Transformer paper and compare its diagram with a modern LLM implementation, the normalization boxes may appear on different sides of the additions. The original Transformer used what is now called post-normalization. A sublayer computed its result. That result was added to the residual path, and LayerNorm came after the addition. GPT-2 moved normalization to the input of each subblock. LLaMA also normalizes before each transformer sublayer and uses RMSNorm, a simpler normalization rule based on root mean square scale. This arrangement is commonly called pre-normalization. So which diagram is the transformer block? Both are legitimate transformer designs. They place normalization differently. For this film, our main animated floor is a common modern sequential pre-normalized decoder block. Normalize attention, add. Normalize MLP, add. We label it so the visual does not pretend to be universal. LayerNorm and RMSNorm also differ internally. LayerNorm centers and rescales features. RMSNorm rescales them without the same mean centering step. The distinction matters, but neither operation is a semantic judge. Normalization does not decide that it means piano. It prepares activation patterns for the learned sublayers around it. The furniture changed between architectures. The floor plan still contains the same core relationship, cross-position update, per-position update, residual routes, and a stack of evolving states. Send the output of this floor into another block, then another. The blueprint repeats, but the learned weights usually do not. Each layer receives a state already changed by every layer below it and learns its own updates. On an early floor, attention might connect nearby grammatical clues. Higher in the stack, the representations can support more contextual and abstract distinctions. That is a useful intuition, not a license to assign one clean human concept to every floor. We understand the architecture more clearly than we understand every computation learned inside it. Now, accelerate the tower. The cyan stream climbs. On each floor, information fans across positions and returns as an update. Then every position folds through its private nonlinear workshop and receives another update. The direct route remains visible through the entire stack. With each pass, the state at it becomes less like an isolated token embedding and more like a context-shaped representation useful to the model's eventual prediction. That is the payoff hidden inside the title. The engine is not one magical attention map. It is a repeated update loop. Attention communicates. The MLP computes within each position. Residual paths carry the evolving state. Normalization keeps the operations trainable and usable. Depth gives the model many chances to refine the representation. But our sentence still hides one piece of information we have not explained. The piano would not fit through the doorway changes completely if we scramble the order of those same words. Attention sees relationships between vectors. Where does word order enter the machine? That is the next episode. Subscribe to Weights and Words if you want to keep climbing through the model one mechanism at a time.